Good morning to one and all. In today's lecture, we'll discuss about the generation of PWM and PPM signals. For the generation of PWM signals, here we have considered input, the MT, that is your modulating signal, and a sawtooth generator. Here, sawtooth generator basically generates the sawtooth wave of frequency fs that act as a sampling signal. Here, it is passed through a comparator where the positive terminal, that is your non-inverting terminal, represent to your MT, that is the modulating signal, and the negative terminal, that is an inverting terminal, represents your sawtooth generator. And here we get the output, that is your PWM output. Now we'll help it with the help of the waveform. Here the comparator compares both the input signal when instantaneous amplitude of modulating signal MT is higher as compared to the REM signal, then the output signal of compare remains high. So your MT is represented by your blue line and this is your sawtooth wave. Here each pulse of PWM output starts with leading edge corresponding to the vertical line of sawtooth wave and remain high as long as MT signal is greater than the REM signal. So these are your REM signal as indicated in the figure. Now in PWM, the leading edge is fixed. While your trailing edge is varied in accordance to the instantaneous modulating signal MT. So hence PWM is associated with your trailing edge. As we can see that for the negative half cycle, it will remain same, the trailing edge. For the positive half cycle of MT, that is your modulating signal, it varies. So there is a difference in the trailing edge. Now at the output of PPM, we can see that in PPM we will be having fixed leading edge for time ts seconds. So here we can say that the comparator signal output remains high as long as instantaneous amplitude of MT is higher than your RAM signal. So this gives rise to your PWM signal. While the leading edge of PWM signal is always generated at fixed time instant, but the trailing edge will depend on the instantaneous amplitude of MT. Hence PWM signal is said to be your trail edge modulated PWM. So corresponding to each trailing edge of PWM signal, the monostable output goes high for a fixed time decided by its own RC component. Here the PPM, that is your pulse position modulation output, the pulse keeps shifting in proportion to PWM trailing edge. All the PPM pulses have same width and amplitude. So the information is conveyed by changing the position of the pulses. Now coming on to the demodulation of PWM and PPM signals. Here we can see that we'll first convert the PPM to PWM and then we'll use the method of demodulation. Now coming on to the demodulation of PWM and PPM signals. Here we have PWM and noise as an input. It is passed through a pulse generator. After then it is followed by your RAM generator as well as your reference pulse generator. So here we basically generate your PWM, and at the reference pulse generator, here the amplitude and width pulse is constant. Now it is added and here we have the ramp slope, that is constant. It is passed through your clipper and after that it is passed through your low pass filter. Here we get the output of PAM signal and then after it we detect our output. So let's explain it with the help of the waveforms. Here we can say that we have the pulse width modulation along with the noise. So these are distorted signals, that is the input of the detector. After then, when your noise is removed by the pulse generator, then we get the regenerated PWM. Next, we see at the output of the ramp generator, we generate the height of the ramp is proportional to the width of PWM pulses. Means the slope is constant. Now, after it, we'll see there is a delay at the reference pulse generator output. After it, next we will be seeing that when we'll clip our signal at a certain threshold value, then it will be, we will be doing the clipping and we'll get the output of the adder. So it is getting clipped at a threshold level to generate your PAM signal. Now when it is passed through your low pass filter, so the work of the low pass filter is to recover the original modulating signal back from the PAM signal. So this is the output that we'll get at the clipper output. So this was all about your demodulation of PWM and PPM signals. Now we will discuss the detection of PPM signals. Here in PPM signal, first it converts the PPM to PWM. PPM is first converted into PWM, and then we use the method of demodulation to PWM. In this, at the receiver, PPM wave plus noise is passed through a pulse generator and a reference pulse generator that generate your fixed reference pulse. The pulse generator generate your fixed reference pulse while your noise is being removed through the help of your pulse generator. Now it is passed through a flip-flop, that is your SR flip-flop. Here your R is the reset pin and S is the set pin. Now the set pin is set by the reference pulse and it is passed through your PWM demodulator, that is the pulse width modulator. We have already discussed about the demodulation of PWM. Now we can see that we are applying SR flip-flop over here. So we note a point over here that due to the set and reset applied to the flip-flop, we get PWM signal at its output. This PWM signal can be demodulated using the PWM demodulator. So after that, we'll get our original signal, that is the modulating signal. So this was all about the demodulation. Thank you.